Hello, welcome to the course SJPHY1B01 Mechanics 1. The contents of this course is taken from An Introduction to Mechanics by Kleppner and Kolenko. We'll continue to discuss topics from Chapter 2, Newton's Laws. Having familiarized ourselves with the statements of Newton's three laws, it's time now to apply them to understand the motion of classical mechanical systems. So a number of steps are involved in this process. These steps are very easy based on a very simple logic. And once you are familiar with them, they appear almost intuitive. Now the laws as such, you can call them as the information, and the way you apply them onto a system, that is the methodology. Unfortunately, many a time people focus only on the information and not on the methodology, without realizing the fact that without methodology, the information is practically useless. So whenever you learn a new theorem or a new equation, it's imperative that you understand the methodology so that you can unearth the physics behind the system under study. Application of Newton's laws include 5 basic steps. And first one, as I discussed in the previous class, Newton's laws are originally derived for point masses, but majority of the system which we encounter in our daily lives, they are either large systems or systems consisting of large number of particles or point masses. So what you can do is mentally divide the system into smaller systems, each of which can be treated as a point mass. Now you can apply Newton's laws into each of these point mass and understand the total behavior of the system. That's why many a time you find integrations or summation in your equations. For example, if you are studying a system consisting of large number of particles, to each particle you apply Newton's laws, finally add them up so that you can get the overall behavior. Or if you are studying a rigid body or a continuous distribution, take a very small section of the body, treat it as a point mass, apply Newton's law, then you can integrate over the entire body so that you can get the overall behavior of the system. Second step, draw a force diagram for each of the point masses. Now when you draw the force diagram, you can represent the body by a point or a simple symbol and label it. So for example, if I have two blocks A and B, A is sitting on top of B, both are not moving. So I can represent A and B with two dots, and if I say a mass of object A is MA and mass of object B is MB, so these two are essentially 2 point masses. And after representing your point masses, you can draw a force vector on the body for each force acting on it. And when you draw force vector, draw only the forces acting on the body and not the forces exerted by the body on others. Similarly, you draw only real forces, which means the force measured in the inertial frame. In the previous class we said there are also pseudo forces which arises purely due to the acceleration of the frame. So when you draw a force vector, you don't have to include those fictitious or pseudo forces. So in this case, how do I draw the vector diagram or the force vector? I have point mass MA, and what are the forces acting on it? I know that B is going to exert a force on A in the upward direction. I call it as F1. By Newton's third law, an equal and opposite force will be exerted by A onto B, but as I said, you don't consider forces exerted by the body itself while drawing the force vector, so you don't have to bother about that force. Then A has a finite mass, which means the force of gravity is going to act on it. In other words, there is a weight acting in the downward direction, so you call it as WA. So this is the force diagram for point mass A. Similarly, for point mass B, there is a force exerted by A onto B in the downward direction. You call it as F2. Weight WB acting in the downward direction, and block B, imagine that is kept on a tabletop. So the surface of the table is going to exert a force N in the upward direction. Once again, from Newton's third law, there will be an equal and opposite force exerted by B onto this tabletop, but you don't have to consider that force while drawing the vector diagram. So these are the force vectors acting on each of these point masses. Third step, introduce a coordinate system or frame of reference, and the coordinate system must be inertial. Why? Because we are representing true forces, and true forces are always measured with respect to an inertial frame. And with the force diagram as a guide, write separately the equations of motion for each body. Equation of motion is nothing but Newton's second law, F is equal to ma. So for each point mass, using the force diagram, you can write the equations of motion. So for example, if you want to write down the equation of motion for point mass A, so we know that F1 and WA are the forces acting on it. So left hand side, total force is F1 plus WA, which is equal to mass MA into acceleration AA. Now, the force will have multiple components. For example, if you take a two-dimensional case, I can draw a coordinate system, preferably a Cartesian coordinate system. I have x and y axis here. I cap is the unit vector along the x direction, and j cap is the unit vector along the y direction. And as you can make out from the force diagram, forces act only in the vertical direction or along the y direction. So F1 equal to F1 j cap, and WA is minus WA j cap. So by convention, we take the downward direction as negative and upward direction as positive. Now you can substitute these back into this equation. So as I said, since I am considering a two-dimensional case, I have x and y components. And what is the equation of motion in the x direction? Obviously, there is no force in the x direction. So left hand side is 0. So 0 equal to ma into aax, where aax is the acceleration along the x direction. And when it comes to y direction, F1 minus WA equal to MAAA1. The first equation is trivial because the left hand side is 0. There is no force acting on it. So you are not going to get any insights about this motion. So you can just omit it and focus only on the vertical direction. So since we are now talking only about the vertical direction, you don't have to mention y explicitly. So I can write F1 minus WA equal to MAAA. Similarly, what is the equation of motion for B? So I have N acting on the upward direction, positive direction, and WB and F2 acting in the negative direction. So left hand side is N minus F2 minus WB equal to MB into AB. So these are the equations of motion. Now fourth step, if two bodies in the same system interact, the forces between them must be equal and opposite by Newton's third law. So these relations should be written explicitly. So we have two interaction forces, F1 force exerted by B on A, similarly F2 force exerted by A on B. From Newton's third law, F1 is equal to minus F2, or if you are considering only the magnitude, F1 equal to F2. So in addition to equations of motion, you have additional equation from Newton's third law. Fifth step, in many problems, bodies are constrained to move along certain path. Each constraint can be described by a kinematic equation known as constraint equation. So write each constraint equation. Now in the present case, The two blocks on the tabletop, they experience no vertical acceleration because there is no movement along the vertical direction. So this is a constraint with respect to vertical direction. So the constraint equations in this case are acceleration of body A and B along the vertical direction or y direction equal to 0. So I can write mathematically AAY equal to 0 and ABY equal to 0. So you can find constraint equation in almost all mechanical problems. For example, if you want to study motion of a train. So train is moving towards the right with an acceleration 10 meter per second square. Imagine that train has three compartments X, Y and Z. So it's understood that all the three compartments will have same acceleration as the train, right? So if you take motion along the horizontal direction, I can view it as a constraint. So the constraint equation in this case will be acceleration of body A, AX equal to acceleration of body Y, AY equal to acceleration of body Z, AZ. Okay. So in addition to the equations of motion and Newton's third law, you have constraint equation also coming into picture. Now once you have written down all these three types of equation, when you go through the variables involved, you will find that some of the variables are known, the values are known to you or you can measure, and some of them are unknown. The force equations and constraint equation should provide enough relations using which values of every unknown variable can be determined. So if you list out all the equations we have derived so far, we have two equations of motion and one equation from Newton's third law and two constraints equation AA equal to 0, AB equal to 0. So I have 5 equations in total, and which all parameters I know. These two acceleration, their value is 0, so I know them. Mass of A and B I can measure, so that is a known parameter. And weight of these two, mass multiplied by gravity is the weight, so weight also I can measure. So what are the unknowns here? N, F1, F2. So I have 3 unknowns and 5 equations. Now the thumb rule of equation solving is that number of equations should be greater than or equal to number of unknowns. Only then you can solve them conclusively. For example, take this equation x square equal to 9. You have one equation and one unknown. X is the unknown. So you can easily solve it. You will get value of x equal to square root of 9, which is plus or minus 3. So you can solve it conclusively. On the other hand, if you take the case of an equation with two unknowns, one equation, two unknowns, x plus y equal to 10. What are the solutions? X could be 10, y could be 0. That is one solution. X is 0, y is 10. Another solution. X is 5, y is also 5. Another solution. You have infinite possibilities here. In other words, you cannot determine the solution conclusively. What's the reason? Number of equation is not greater than or equal to number of unknowns. On the other hand, if you take this system, x plus y equal to 10, x minus y equal to 0. You have two equations, two unknowns. You can solve it conclusively. You add these two, you get 2x equal to 10. From that, you can get x equal to 5. Substitute for x in any of these equation. For example, in the first equation, 5 plus y equal to 10, which means y equal to 10 minus 5, 5. So x equal to 5, y equal to 5. So whenever the number of equations is greater than or equal to number of unknowns, you can solve the system conclusively. So that's the reason why we are adding constraints equation to the force equations. Otherwise, what will happen? Maybe the number of equations will not be sufficient. Now once you have 3 unknowns and 5 equations, you can very easily solve them. For example, we know that AA equal to 0. So in the first equation, right hand side becomes 0, which means F1 equal to WA. From third equation, I know that F1 equal to F2. So I can conclude F1 equal to F2 equal to WA. Similarly, in the second equation, AB equal to 0, right hand side is 0. So N equal to WA plus WB because F2 equal to WA. So you can solve them very easily. So these are the 6 basic steps involved in the application of Newton's law. What we are going to do is we will apply these to some of the example problems so that you will get familiarized with the methodology of Newton's laws. First one is an imaginary problem. It's known as the astronaut's tug of war. Two astronauts A and B, initially at rest in free space, pull on either end of a rope. The maximum force with which A can pull is Fa, and maximum force with which B can pull is Fb. Their masses are Ma and Mb respectively, and the mass of the rope Mr is negligible. Find their motion if each pulls on the rope as hard as he can. So I have astronauts A and B pulling on either side of the rope, and I will assume that the force is acting on the same line, so this is essentially a one-dimensional problem. So you have the rope here, you can represent with a point dot here. So this is a point mass with mass equal to Mr, which is negligible. So Fa and Fb are the forces exerted by the astronauts on the rope. So Fa acts towards the left, Fb acts towards the right. And from Newton's third law, the rope is going to exert an equal force in the opposite direction. Okay, so I call this as Fa prime and Fb prime. So Fa prime is the force exerted by a rope onto astronaut A, and Fb prime is the force exerted by the rope onto astronaut B. So these are the directions of Fa prime and Fb prime. And we can choose a sign convention. All the directions toward the right is taken to be positive. Consequently, all the left directions are taken to be negative. So this is a convention. You can choose any sign convention. For example, you can choose left as positive and right as negative. Nothing wrong here. But once you choose a sign convention, be consistent with it. Every time you apply that. So in the previous class I said all the downward directions are taken as negative and upward direction as positive. You can choose the opposite. You can choose downward direction as positive or upward as negative. But once you choose that, be consistent with that. Okay. Now, it's time now to write down the equations of motion, the Newton's equation from the third law as well as the constraint equation. That's what the methodology says, right? So first one, the Newton's third law, I know that the force exerted by the astronaut on the rope will be equal and opposite to the force exerted by the rope onto the astronaut. So I can write Fa prime equal to Fa, similarly Fb prime equal to Fb. And the equation of motion on the rope, so Fb acting in the positive direction, Fa acting in the negative direction, and if we call the acceleration of the rope as AR, I can write Fb minus Fa equal to Mr AR. Only motion along the line of the rope is of interest, and we omit equations of motion in the remaining two directions. So there are no constraints here. On the other hand, if you are considered motion in the vertical direction, then I can write a constraint equation. Acceleration in the vertical direction is 0. But now, since we are not considering those directions, we don't have to write any constraint equation. As I said earlier, the mass of the rope is negligible, so you can equate Mr to 0. So your equation of motion gets simplified as Fb minus Fa equal to 0 or Fb equal to Fa. The total force on the rope is Fb to the right and Fa to the left. And we have found that these forces are equal in magnitude, and hence the total force on the rope is 0. So even though we have derived this result specifically for this case, this is a quite generic finding. So in general, the total force on any body of negligible mass will be negligible or effectively zero. What's the reason? F is equal to ma. So if m is almost zero or negligible, acceleration F by m is going to be really large or infinity. So a finite force acting on a zero mass would produce an infinite acceleration. So imagine a situation, you have a ball of 100 grams and you are pushing it with a force of 100 Newton. Now, when you apply a force, the force is not applied instantaneously. It takes certain time to apply the force, right? For example, it takes 1 millisecond for you to apply this force. Even though 1 millisecond is a very small time frame, it is not quite instantaneous, right? So if you divide 1 millisecond into 1000 microseconds and monitor the force at each of the microsecond interval, what do you find? Initially, there is no force, and gradually with each microsecond, the force is increasing. Finally, at the end of 1000 microseconds or 1 millisecond, you will be applying a force of 100 Newton. Right? So if you take the first 1 microsecond, you will be applying a force of 0.1 Newton. In the second microsecond, you will be applying 0.2 newtons and you keep increasing that way. Now imagine that the weight of the mass of the ball is negligible or almost zero. What happens? In the first 1 microsecond, you are applying a force of 0.1 Newton. But mass being negligible, the acceleration is almost infinity or very large, which means by the time you apply 0.1 Newton, the ball gains considerable acceleration that it moves far away from you. Now in the next microsecond, you are supposed to apply a force of 0.2 Newton, but the ball has reached so far that it is not going to experience any force from you. So you can never apply more than a negligible force on a negligible mass before it accelerates out of your reach. That's why for all practical purpose, you can conclude that the total force on any body of negligible mass is effectively zero. Now from the Newton's third law, I know that Fb equal to Fa, from Newton's third law, I know that Fa prime equal to Fb prime. The forces are equal and opposite. So from these two, I can write the accelerations of the two astronauts, AA equal to force exerted by the rope onto astronaut A, Fa prime divided by mass of the astronaut Ma. This is a positive acceleration, which means it's pointed towards the right. And acceleration of astronaut B, this is minus Fb prime divided by Mb, or Fb prime is same as Fa prime, so this is minus Fa prime divided by Mb, and the negative side indicates that this is working towards the left. So this is how you apply Newton's laws to analyze motion of a classical system. So here we are considered a single rope. Imagine your system consists of multiple components. Then how do you apply the methodology? So consider the case of a freight train. Freight train means goods train. So I have a goods train with 3 compartments or 3 freight cars, each having a mass m. And the train is pulled by an engine which uses a force F towards the right. Assume that the friction is negligible. Calculate the forces on each car. So first let's write the constraint equation here. Since the 3 compartments are joined, they are constrained to have the same acceleration. So what is the acceleration? you can calculate acceleration by dividing the total force F divided by with the total mass, which is m plus m plus m, 3m. So acceleration is F by 3m, and acceleration is same for all the 3 cars. Now assume that the weight of each car is W. So weight is always going to act downward. From Newton's third law, there is equal and opposite force in the upward direction, called that as N. But here we are mainly bothered about the horizontal movement, and as we know, when a train is moving, there is no vertical movement. You can forget about the jerks here. So in the ideal situation, there is no movement in the upward direction, which means the upward force N is compensated by the downward force W. So N equal to W. So since these two forces are equal and opposites, there is no vertical acceleration. So we don't have to consider the vertical forces while writing the equations of motion. Okay. Now let's draw the force diagram for the last car. So I have N acting in the upward direction, W acting in the downward direction. We are not going to consider these two. And the last car is pulled towards the right by the middle car. Let's say F1 is the force exerted by the middle car on the last car. Okay. So I can write F1 equal to mass into acceleration m into A. A is nothing but F by 3m. So F1 equal to F by 3. What about the middle car? The middle car is pulled towards the right by the first car, call that force as F2, and it is pulled towards the left by the last car, and this is F1 prime. And from Newton's third law, I know that F1 equal to F1 prime. So as I said, the right hand direction is positive, so the equation of motion will be total force, which is F2 minus F1 prime equal to mass into acceleration. F1 prime is F1 from Newton's third law. F1 is F by 3. So I can rewrite the equation of motion as F2 equal to ma plus F1 prime, or ma plus F by 3. Substitute for acceleration, you have F by 3 plus F by 3, which is 2F by 3. Moving on to first car, which is straightforward. It is pulled towards the right with the force F, and the middle car pull it towards the left with force F2 prime. But from Newton's third law, I know that F2 equal to F2 prime, which is 2F divided by 3. So the total force experienced by the entire train is F, and the forces on each individual car is F by 3. So you have F by 3 plus F by 3 plus F by 3, which is F. So as the number of cars increases, the force exerted by the engine is going to increase. Now the takeaway lesson from this entire exercise is that for a compound system to accelerate, there must be a net force on each part of the system. So that's for today. In the next class, we will discuss a couple more examples where we can analyze the motion of the system by carefully applying the Newton's laws. Thank you.